So as promised, I now go into details in routing. So last time I introduced all these steps, which you can find in any wireless mesh routing protocol. So let's start with the first one. You see there's neighborhood discovery written very small. Not talk about this too much because it's super easy compared to link adaptation, which is more complex there. It's basically a matter of recognizing another node which you received a message from and keeping this probably in a list. So before we start with link adaptation, a quick note on Unicast and Broadcast. This is very important that this is clear before we start talking about link adaptation. So we can have Unicast and Broadcast in two different layers. And what they mean there is fundamentally different. So first of all, link layer unicast means that a node addresses one other node. I start from D there, which is the destination in other cases, but maybe, yeah, it's not important, I guess. Broadcast would mean that any node that receives the message would also process it, which is not the same in unicast. If a node receives a message in link layer unicast, it's not destined for him, it just drops it. Then the network layer unicast and broadcast are routed unicast and broadcasts, or potentially routed. So we have these graphs as examples there. It just means that in the layer 3, so network layer unicast, just one node is the destination of a stream, while in broadcast, any node in the network is the destination of the stream. What's important here to note is that we can use any combinations of those to reach node, to have a stream ongoing. So we can use link layer unicast to perform a network layer broadcast, as it is in this example here. But we can also use link layer broadcast to do network layer unicast, while there are combinations which are more efficient. So for example, if you want to reach every node in the network, meaning that you want to perform a network layer broadcast, it might be more efficient to use link layer broadcast to do that, because you implicitly reach other nodes with it, if it's possible. So speaking about link types, some link types, for example Wi-Fi, cellular, so 4G or 5G, or Bluetooth, operate in bands of the electromagnetic waves, which are implicitly broadcast. So you reach other nodes if you want to or not. Surprisingly, also PLC, so power line communications, is also a broadcast medium. So if you communicate over the power lines that go to our power sockets, you also reach other nodes. So surprisingly, those broadcast media are very often used as a unicast medium. So even if you reach other nodes, these two here in this example, they'll drop the message, and the link adaptation is done only between those two here. This means that only one link adaptation also is necessary. And it is often built in, for example, the Minstrel algorithm, which is used in many 802.11, so Wi-Fi implementations. This wire abstraction in a wireless medium is also used in Batman, also because the rate for a broadcast is harder to choose, because you just have multiple receivers to adapt your link to. Then there are media which are non-broadcast by nature. Very often those are wired connections like Ethernet. but you can also beamform wireless links which might still bother other nodes with some interference, but essentially just reach one. Also, this is possible in Batman. So how do you adapt to a link that you don't know if you don't use a built-in mechanism? So if the protocol should do the link adaptation itself, for example, like in layer 2 broadcast in Wi-Fi, where there's no acknowledgement from every of the receivers if it has received a message, like it is in Unicast, and there's also no built-in rate selection. Well, you can always do a broadcast in the same rate, but it might not be efficient, where there are a lot of rates to choose from. So what we can see here is we'll have 11 or 12 different modulation and coding schemes there, and this is only for one spatial stream. So even if you use a built-in rate selection, you might still want to record statistics about how well a link performs, because even if there is a rate adaptation, a link might not really work well. And yeah, I'm going to show you how now. So you could use something like the received signal strength indicator for that, but it's very efficient to just record statistics about received packets and feed it back. By that you record an empirical packet success probability. So what I have here is the function for this empirical success probability, which can, for example, be done by just recording a packet reception ratio. So it's not the same because the channel changes quite quickly sometimes, and using very old data of received and sent packets might not be accurate, but it's a way. By this you can put weights on the edges in the graph here. On that note, when I was preparing this video, I actually saw that I never really talked about the graphs that I'm showing here. So let's start with a little excursion on graph theory and networks. This might be new to you. Some of you might already know what I'm talking about, but it's a very common way to represent networks using graph theory. So sometimes I say routers, sometimes I say nodes, sometimes I say links, sometimes I say edges. So the usage of graphs for representing networks has one very important advantage. So you can calculate with it. Normally a router or a switch is a node or vertex. So you have a little circle and a letter in it. And all the vertices in a graph are the set of all vertices. Then links, wireless links in our example, are these edges. And a full graph is nothing else than the combination of all vertices and edges, where the edges connect the vertices or nodes. So as I said, you can put weights on these edges, and thereby you can calculate with it. So if you connect these edges together, then you can use a mathematical operator to do that. So for example, if in your graph the connecting operator is times, then 1.5 times 2 is 1, or you can use a plus for it. It just very much depends on the way you're using the graph here. The important thing is there's no connection between I and K here, as there might be no Wi-Fi link between those two routers. So coming back to our example here, now if we notice that only half of the packets are received by this node that are sent from node D, we'll have a packet reception ratio of 1/2. It's quite easy, right? We can also use that to describe paths through the network. And this is where it gets really interesting, because if only half of the packets are received by this node and only 1/3 are then received by this node, again, I messed up with the directions here, so that's source and that's its destination. In this example, it's the other way around. We can calculate the total packet reception ratio of the path. In this example, we'll have half the packets received here, and half of those packets are received by the end node of the stream. So the total packet reception ratio would be 1/6. That's a good example how cross-layer optimization works, as I was talking before. Because judging about multiple hops is essentially called routing. And this metric is actually used in Batman and is called traffic transmit quality. So that's actually a bit more accurate than the metrics that we used before. Well, because before normally the hop count was only used. So we can easily see that the hop count between those two nodes is always 2, because there's no direct connection between them. If we use the shortest paths here, we can also always use longer paths. The thing is that if we use those link statistics, if we gather statistics about how well the links are performing, we can operate much closer to reality, because the loss rate might not be 0, but 1/2 or 2/3 here. So there are a lot of those link metrics that are built by recording link statistics. A more well-known link metric than transmit quality is called ETAX, which is the expected transmission count. That's very much the same, but very much the same way to build it, but only the reciprocal of it. So it's 1 divided by the traffic quality of the link. The thing is, it's not the same for the path here. The mathematical operator that connects those connects ETX values is the plus sign. So the ETX for the full path would be 5 here, and not 6. So we can see that the hop count is a very primitive way to connect the length of paths, but it's a bit inaccurate. If we record packet loss probabilities, then we can do that much more accurate. But if the packet loss is 0, it's the ETX and hop count, or also traffic quality and hop count, are the same, which means that both are generalizing the hop count for loss probabilities that are not 0. As I showed you before, there are a lot of different bit rates that can be used in Wi-Fi. It's the same in many other physical layers. And to account for that, the ETT, the expected transmission time, was invented. Again, it's easy to calculate. It's just the bit rate multiplied by the ETX for that link. Again, we can see that if we use a bit rate of 1 bit per second, ETX and ETT are the same. So ETT generalizes ETX for arbitrary bit rates. Then there's the WCET, the weighted cumulative expected transmission time. This is a metric. This is for which is for multi-radio environments. So consider the changed graph on the right. So the two links that are here can now be of a different radio type or a different frequency band. As an effect, they're non-interfering, which just means they can transmit at the same time, which it wasn't the case before. In order to reflect this within the distance metric, the WCET was invented. So in this metric, different radios can transmit, and the metric can be dominated only by the weakest link, which makes sense for multi-radio environments. However, because this is a very abstracted view of reality, there's the weights here, beta, they are called, and they weight the traditional ETT path metric with the weakest link in the chain. So if we say that we only want the weakest link in the chain to be our metric for the path, this would be 3 for this case. So if we only have one radio, this metric also generalizes is the same as ETT, and thereby generalizes the ETT metric for different radios or channels. So what's the actual task of this of these distance metrics? The actual task of them is to scalarize the network order in respect of a certain source or destination node. So let's say one arbitrary metric has assigned those values, those distance values, to any of the nodes here. So the distance to D to itself is obviously 0, and then we have some order here. As an effect of that, we have a scalarized order in the network. This means that any node can distinguish if another hop is going towards or away from the to the destination node. We also name this downstream, so towards the destination, or upstream, away from the destination. So this makes the general direction clear. If a node receives a message from a downstream node, it's not helpful to retransmit it. So for example, if the node I receives a message from K, it's definitely not helpful to forward it again, because if it's destined for D, it's not going in this direction. Whereas these distance metrics do not really answer the question which of I or K should forward the message if they receive it from S, or both. So we clarify this in the next section. But before that, we'll see a short demo on how the concepts I previously explained are implemented in Batman.